I wasn't even sure, you know.
Okay, before we get started with the afternoon talk, quick announcement. Karel will give a very informal overview of, or a description of the Jim Simons Lando Ginsberg for the new course 1 more read state, if I remember correctly. And this will be just sometime after the talk, I guess, 3:30 or something like that. So everybody, it will be very informal. Everybody is very welcome to join if they want. Yeah, yeah. And before that, we'll have horsdal from the Vita, who will talk about sharp fractional charges in the liquids.
Thank you. So, I'll begin by thanking the organizers for giving me the opportunity to talk about this work. And this is the last day of the program, so I'm ready for one more of these talks. And I noticed that, well, the talk didn't start out very well because the first mistake has been spotted already, but let's see how it goes. So, what I'm going to present to you is something I've been doing together with Magne in Oslo and Hans here at SU. And it is about fractional charges in Luttinger liquids, and there have been some papers around that claim that in this Luttinger liquid, which I will introduce, there exist excitations which carry fractional charge. And we wanted to look more carefully into this claim to see if we could get a better understanding of it and to understand whether these charges are really sharp or not. So I will begin by saying a few introductory words. And then I will introduce to the Luttinger model. It will be quite a brief introduction, but I hope from that I will be able to motivate you why this is interesting. And then I will talk about fractional charges, and then I will show you some examples that we cooked up where we show that there are fractional charges in the system. And then finally I will start to discuss whether these charges can be considered as sharp or not. So, yes, probably most of you at this conference are quite familiar with Luttinger liquids. So it's a one-D theory of interacting fermions. And this theory has gapless excitations, and that is quite important. And like physical realization is carbon nanotubes. It's been used to describe transport properties of these nanotubes, and also, as we've seen here several times, the edge of the quantum Hall system. And these Luttinger liquids are characterized by a parameter G, which I will say more about later. And there have been some suggestions in the literature that this Luttinger liquid carry excitations with this fractional shard, and this shard is dependent on G. And this G is related to the interactions in the fermion model. And as you know, other systems which have fractional charge, for instance, the excitations of the quantum Hall effect, they take place in a system which is gapped. But as I said, the Luttinger theory is gapless. So for the gap system, this gap suppresses low frequency oscillations, so you are able to have sharp fractional charges. But with gapless system, this is not so clear, and we will see that not even the vacuum is sharp. So if you try to measure the charges in a localized region in the vacuum state, you will see that you have fluctuations going on. So just to say what I will get into later is that we will define sharpness of charge. We say that a charge is sharp if the variance is identical to the ground state variance of the charge operator. So now let's start with the Latinger model. There might be some nasty equations floating around there, so for those of you who have seen it before, this will be very nice and cozy and familiar. For the rest of you, I will try to tell you what is the important physics in this. So we start out with a Hamiltonian like this, where we have a kinetic term. You see it's quadratic in the momentum, and you have an interaction term here. And we'll make a plot of the dispersion of this kinetic term. It has a parabola like this, and the ground state will then consist of all the momentum states between these two Fermi points occupied. So if you only consider the low energy sector of this theory, you can assume that excitations only take place close to these two Fermi points. And we can then linearize the dispersion at these 2 points. So we end up with a kinetic term like this. And when we do that, we kind of introduce two types of particles. We have excitations close to the right Fermi point, which we characterize by chi equal to plus, and chi equal to minus is equal to the excitation close to this minus k of Fermi point. And as you see on this drawing, I kind of extended these branches all the way to infinity to create an infinitely deep Fermi sea. And that's very artificial, but as long as we only consider the low energy sector, we can do this, because every interesting stuff, or what will be interesting to us, is happening close to these 2 points anyway. So just to start by write down, there is chi, and so that specifies Fermi point. The reason I'm writing it down is because I will introduce another quantum number later on. And well, by playing around with this Hamiltonian, with this linear dispersion, you can Bosonize it, and I will not go into how we do that, but the idea is that you look at the commutator algebra between the density operators in this theory, and you see that it has like bosonic-like commutators. So we can then rewrite all the interesting operators in this bosonic language. So when we bosonize this, we end up with Hamiltonian like this. We see that we have 3 bosonic excitations, and we have this frequency, this energy, omega, and the interaction of this fermionic theory is contained in this omega. And we have 2 other operators. We have an N, a J operator, which I define here. So N gives the total number of fermions added to the close to these 2 Fermi points, and J is the difference between the number of electrons sitting at the right and left Fermi point. And then we have 2 velocity parameters, Vn and Vj. And Vn and Vj, they also depend on the interaction in the fermionic description. So from the definition of N and J, you see that they have to be restricted by the Fermi condition so that N plus minus J are even. And by considering Q close to 0 limit of this, we can rewrite it in a more field theoretic form like this, where we have 2 bosonic fields called theta and phi. And here this G parameter pops up, and it's defined as just a ratio of these 2 velocities I showed you on the other page. And we also have a velocity parameter, that will not be so important. It's this G is quite important. And you can show that if you don't have any interactions between these two chi particles, that is between the particles close to the two Fermi momentum, then G will equal to 1. But if you have that kind of interaction, G will be different from 1. And you don't see that N and J operators anymore. And that, the reason is that they are hidden in 0 modes in these theta and phi fields. And the way they're hidden is that these fields are now restricted by the Fermion number. So you have this quasi-periodic boundary condition. So we assume that we are in a circle. So if you go around the circle, theta will change by J, and phi will change by N. And remember that J and N are integer numbers. You can write down a linear combination of these theta and phi like this. And when we look at the equation of motions for this field, we see that they separate. So theta plus is moving to the right, and theta minus is moving to the left. And this is the expression. It's not that important, but this q plus minus is quite interesting, and it's defined in this way. And this q plus minus have been interpreted as total chiral charge. And you see that when G is different from 1, that is, you have interaction between these two Fermi points, or particles close to this different chi, then you will have a charge that is not even integer. And one way to see that is, as we've seen several times here, that you can write these electron operators as vertex operators in this theory. You know that you have the exponential of these theta and phi fields so on. And what was shown by Pham et al. Is that when you write the electron operator, it kind of splits into a product of two operators, which they have defined as d plus minus, q plus minus, which looks like d to the minus I phi g plus minus plus minus x. So they then claim that this operator creates excitations which carry fractional charge. But there are some problems with that interpretation. First of all, theta plus minus do not satisfy the boundary conditions. And you can see that clearly from here, since this q plus minus is no longer an integer, when you go around the circle, you will not change theta plus minus by an integer. So this is then not a well-defined operator to create these excitations. And the other thing is, if you try to look at the commutator between this n and j operators, the commutator between n or j between the Hamiltonians, see that it's 0. So that means that they do not move. So the n and j operators do not propagate. So therefore it's a bit strange to kind of consider these as chiral charges, since they have no motion at all. So this is just more like a background to see what has been proposed in the literature. And now that I introduced the Luttinger theory to you and told you somewhat that have been done here, it's time to see if we can cook up some kind of fractional charges ourselves. And to do that, we find it quite useful to use a 2D representation of this 1D system. So a 2D interacting electron gas in a Field-Dano level, that is nu equals to 1, and you have a harmonic confining potential in the y direction, we can show that this is equivalent to a 1D system described by Luttinger Hamilton. And you can then have a mapping between the 1 and 2D systems like this. So here we have the off-diagonal 1D density, and you map it to 2D by performing these kind of Gaussian-like integrals. Or you can write it as like this. We have kind of same looking integral, but this is the Wigner function. So this can actually be seen as a phase-space representation of this 1D system. And it's phase-space in the sense that this y-coordinate then corresponds to the momentum in this system. And it's quite easily to see that. You know that if you solve the Landau problem in the Landau gauge, you know that single particle eigenstates will just be plane waves in the x direction, and you will have in the y direction this harmonic oscillating ground states, which are just have this Gaussian shape, but they will be shifted away from the origin by some amount. So that means that you see that we have a correspondence between y and k, so they correspond to each other. And when you look at this picture, it makes it natural to introduce two quantum numbers. I've already introduced chi, which represents the Fermi point, but we can see when we go to this 2D representation that it also represents the edge. And we can introduce a gamma, which is now the chirality. And by chirality I mean in which way excitations travel. And we would guess that, well, if you have something going on at the upper edge, that is chi equal to plus, that's the right Fermi point, you would assume everything moving to the right. But that is not longer the case when we have interaction between these two edges. So for chi equal to 1, then gamma, for g equal to 1, then gamma and chi correspond to each other, but when g is different from 1, that's no longer the case. And as we'll see, we can see that you have this difference here. It can be seen as some kind of a polarization effect. So how to extract this gamma quantum number? Well, we start by looking at the time dependence of the Boltzmann density operator, which I've written here. And by looking at time dependence, we can extract the chirality. And by doing that, we end up with something like this. Where we take the q goes to 0 limit. I'll say a little bit more about this limit later. And so we consider the Hermitian combination here, and we take the q goes to 0 limit, and that is our localized charge operator. And well, this B operator is just some of these sonic operators. And taking this q goes to 0 to define the local charges is closely related to what was considered by Heino and Kuhn in a paper where they looked at Fermi liquids. And so why is this a localized charge? All I need to see is that we want to calculate the charge in some finite region of the system. So we have the ring, and then you make some kind of box, so you integrate the charge over some finite region. And then you take this box to be very large. That means that you kind of sum up all the charges that have some kind of motion. If you take q equal to 0, that is just the total integrated charge, which is fixed by the boundary conditions. So we want to see what is moving in the system, and therefore we take the q goes to 0 limit. And this limit does not necessarily have to be continuous, as we will see.
Are you going to tell us how we get rho chi gamma from rho chi q?
No. But what you do is you write down this expression. And well, if you want to look at, let's see. So, say that you have x of t, and then you can write this as q chi of t times e to the I cube x. So you're looking at this Fourier expansion of this one.
Yeah.
And when you know how this thing depends on time, you can extract in which way it's moving. Because this thing here is, I don't remember the exact form, but this is linear in this EQ operators, and you know that since you have free bosonic Hamiltonian, time dependence is e to the I qt plus, well, I think it's plus up there, and then you can extract the chirality from that. So that's actually what we're doing, and when we've done that, we take this Hermitian combination and we take the q goes to 0 limit to define this local charge operator. So we can then define local chiral edge charges by summing over these two edges. We get the total local chiral charge, and by summing over these two chiralities, we get the local edge charge. And you see that I put a bar over this operator, and that means that these are operators that gives you some kind of localized quantity. And to be distinguished from this n and j operators, which are the total total integrated quantity. So, first example is what has been also studied by Pham et al. So, we inject an electron and close on one of the edges, say chi equal to plus. So the state after injection is given like this, so we have some kind of operator that creates an excitation in G, but G is the interacting ground state, but this G is in general different from 1, and this operator is just an electron creation operator, which is modulated by this this wave function here. And this bosonic framework is very powerful, so it makes it possible for us to kind of do these calculations quite easily. So we can then find the chiral charges. And we end up with this when we take the expectation value of this local charge operator. So just to remind you what was claimed by Pham et al. Is that they have this q plus minus is equal to 1/2 m plus minus g times j. And I know bar because this is not related to these local properties. And you see that what you find here do indeed agree with what is their claim, because we insert something at the right Fermi point. That means that n is equal to 1 and j is equal to 1. So we then end up with q plus here, should then be 1/2, 1 plus g, and q minus 1 minus g. So our result there agrees with their analysis. But the important difference is here we consider this local charge defined by taking this q goes to 0 limit.
Actually, so just to clarify, you have this picture up here
Yeah.
of a charge on the upper side and sort of zero charge on the bottom
Yep.
side. In terms of those, which one is 1 plus G and one less G, does
Yeah.
that ratio come out?
Now, well, Q plus is the total charge moving to the right. So it's this combination. And Q minus is this thing here.
And that's broken the symmetry of left and right.
No. What do you mean?
Right, so the top edge is sort of naively all moving left, and the bottom edge is naively all moving right, and the bottom edge is naively all moving the other way, right?
No, you see on the lower edge you have two things moving in opposite direction, and they both carry opposite charge.
If it was non-interacting, the top edge will all move to the right, the
Yeah.
bottom edge will all move to the right. And I turn on the interaction, and I have both charges moving in both directions on both sides.
Yeah.
Right? So what is now, you say that Q plus is the total charge moving to the right,
Yep.
and the in sort of an eigenstring, Q minus is total charge moving to the left in eigenstring. Where did I break the symmetry between left and right in this problem?
Not really see.
Why isn't my system completely symmetric if I...
But you
Well,
insert
you
this
insert
charge
something
on
on the
the
edge.
edge.
Oh,
So that's
okay, there's a total charge. I see
Yeah,
the total charge is on, okay, total charge. plus-
So you start out with this bump on the top,
Okay.
and then this separates.
Okay, okay.
So we see that from this picture, we see that right moving stuff is not only localized to the upper edge. There's something going down here as well,
Yeah.
and that is because you have an interaction between these two edges, and that is due to this G being different from one.
Okay, thanks.
Thanks for asking, it's quite relevant. So this picture shows what we start out with. This is our initial state, and then it separates, and then we calculate these quantities. And so this is total right moving charge, well, the total local right moving charge, and this is the local left moving charge. And as I said, this agrees with the expression for Q plus minus written down there. And you can also calculate the local edge charges, which will be the sum of this one and this one. And you see that indeed it sums up to 1 on the upper edge and 0 on the lower edge. So this also agrees with the expression for n plus minus. So in this case, the particle is injected locally and no background charge is created, and also this Q goes to 0 limit is continuous. But now we'll do something different that is similar to what was considered by Hannon and Pohl. We inject the electron on one of the edges, but in the non-interacting system. And then the interaction is turned on adiabatically. So our initial state, it looks very much like the previous state I wrote down. You have this ground state, this is the ground state of the non-interacting system, and you have this same psi operator creating some kind of wave function in this vacuum state. But then you have this U operator, and this U operator takes you from the non-interacting system to the interacting system. And so it looks like this. We start out by introducing this particle, and you can then again calculate the chiral charges, and we end up with, which is quite surprising, we find that we have no left moving charge here at all. You find that Q plus is different from what we found in the previous case. And it might seem that charge is not conserved there, but the reason is when you you see this red line, this shows the original edge of the system. So when you switch on the interaction adiabatically, you get a shifting of the edge. So some background charge has been created in this process, and that is the reason that there seems to be some kind of charge missing. And you also see that And it kind of makes sense that we don't end up with something left moving, because we start out with something right moving and then adiabatically switching on the interaction. Then we cannot create anything that moves backward in this adiabatic fashion, so we only end up with something right moving.
Sorry to keep interrupting, but
Yeah, no.
so what is the definition of adiabatically turning on the direction here? I mean, did I put in the system and I let it propagate along and while it's
Well,
propagating along,
it's
I turn
given
on?
by this U operator here, which is an operator that takes you from interacting description to non-interacting, or vice versa.
I mean, should I think of this as this thing is propagating along the edge, and as it goes along the edge, the attraction gets stronger and stronger?
Yeah, I think you can think about it that way, and you get the shifting of the edge as it moves, and something builds up down here. I think that's probably the best way of thinking of it. Yeah. So we see that we have no splitting of the initial charge distribution into a right moving and a left moving component. And as I said, a constant background charge has been created to account for the fact that the local charge is not preserved in this adiabatic process, because in this case, this Q goes to zero limit, it is not continuous. And we can calculate the local edge charges, and we see that indeed it's not, n plus is not equal to 1, and n minus is not equal to 0. And yeah, as I said, this corresponds to discontinuous transition when Q goes to 0. So as a third example, we will not inject anything at all. We'll just introduce some potential in our system, which is given like this. So to the Hamiltonian we add this term, which is just a potential that couples to the density. And then we turn it on. So some charge will be attracted by this potential to create a bump. And when we switch off this potential, this bump is separated into a right and left moving component. And you see that in this case, n plus and n minus is equal to 0, because we don't add any charge at all, we just have a potential. And yeah, again, the picture of what's happening. So we also see here this red line shows the initial edge of the system, but when this potential is switched on, some charge is attracted. That means that the edge falls down on the rest of the system, so the background charge is changed. So again, we can go through this calculation, and we see that all the local charges are equal to this value here, where this W is this integral of this potential around the whole circle. And again, we see that the local edge charges are not equal to the global edge charge, and that shows that the background charge has been created in this process. And what is quite interesting with this result is that we have a G sitting here, but we can put G equal to 1. That means that we would have a non-interacting system, and still we would have some fractional charges. And when we saw that, it was not clear to us whether this was some kind of artificial thing coming up from this specialization procedure. So to kind of check whether we could see something like this in a realistic system, we did some numerics. So we just took a circle, and then at one point on this circle we added a delta function potential and put electrons on this circle, and in this case with a finite frequency, not infinitely deep as we have in this bosonized picture. And then if you look at the density, you see that indeed you have some charge that has been localized by this delta function. And by integrating the charge in some, by using some kind of charge operator that integrates in a region that takes into account all this localized charge, you can see how much charge we end up with there. That is plotted here. So the different parameters of this of the strength of this delta function here calculate what is expected from this awesomized description as I've shown on the previous page, and what you find when we calculate the localized charge in this numerical case. And you see that for the quite weak potential, they agree very well, because this line here shows the equality between the bosonic and the fermionic description. So at least this shows that for quite weak potentials, what we get out from this bosonic description makes sense. So what I've been doing until now is just calculate the expectation values for these three cases of a local charge operator. But what we should see is whether these charges are sharp or not. And to do that, we will introduce a new local charge operator, and I will tell you how it's related to the previous definition. But in this case, we really have to work with an operator that looks like this. So it's you integrate this chiral density operator with some sampling function, and the sampling function has this form here. It's just a difference of two arrow functions. So the other width of this sampling function is given by A, and then on the edge here it drops to 0 on the length scale that is given by B. And you can show that in the limit as A goes to infinity, this corresponds to this local charge operator I wrote down earlier. This Q goes to 0 limit. And you can calculate the variance of this operator in the ground state, and you end up with something that looks like this. Quite nice that you can find a closed expression for it, but well, it's a hypergeometric function. But you can take the large A over B limit, and you see that you end up with some logarithmic behavior. So this is the plot of this full hypergeometric function. So we see that when A goes to infinity, this variance diverges. So we have an infrared logarithmic divergence when A goes to infinity, and also ultraviolet logarithmic divergence when B goes to 0. And this B goes to 0 divergence, it's an artifact of this low energy approximation. Because you have to remember that when we did it, I extended the Fermi sea for these two branches of particles all the way down to infinity, but in a real system that is not the case. We will have a real cutoff, and that is a Fermi momentum Kf. So if you try to do kind of similar calculation for a realistic system where you have finite depth in the Fermi sea, you find that this B will be replaced by Kf. So from this we see that we indeed had to define such a local operator, because we cannot readily take the A go to 0 and then the A go to infinity limit, because then this thing would just diverge. So this shows that for a gapless system, like the Luttinger model, the vacuum is not sharp. There will always be some fluctuations, because since you have no gap, you can never get rid of these long wavelength excitations that are floating around. So we will then define sharpness and say that a charge is sharp if the variance is identical to the ground state variance. Because when you have this this nice operator here, you kind of regulate these divergence that show up, and so we then take the A goes to infinity limit, and if we end up with is equal to what we find in the ground state, we say that the charge is sharp. And you can show that all the chiral charges in these three examples, they are sharp in this limit. And one reason that might be the case is that they can all be considered as coherent states. For this polarization chart I showed you about, you can show that is exactly the case for all B operators. This state is a coherent state, but also this sudden injection and this adiabatic injection of electrons, it turns out that the state are eigenstates of these BQ operators, and Q goes to zero limit. So a coherent state will have the same fluctuations as the ground state. So I guess that brings me to the conclusion. So try to show you what the ideas have been when these chiral charges have been discussed in literature, and by using this two-dimensional description that you find very useful to kind of get a picture of what is going on. You've seen these three examples, and they all show different chiral charges. And by defining sharpness, we see that they are all sharp. And there is a reference to the paper. It's on the archive, it will be soon available in PRB. So, yes, that's all. Thanks for your attention.
Questions?
Yeah, I got a bit confused. Maybe I missed something. And somewhere halfway you made this transition to this two-dimensional picture.
Mm-hmm.
And then, as also Steve remarked, it started mattering, the left-right asymmetry. But somehow, the original physical setting was a quantum wire, I guess. Just one.
Yeah.
So you did not discuss that situation with a charge injected from the side, for example.
No, you mean when you just have a like a wire and you inject into that one, yeah. But what you have to remember in this case is I said that we inject close to one of the edges, and that means we inject the particle close to one of the Fermi points. So if you don't inject the particle close to the Fermi point, say that you kind of injected with momentum 0 or something, you can show that what you end up with is actually a superposition of the particle going to the right and to the left. So, and when you try to calculate the variance for such a state, you will see that it's not equal to the ground state, so that is not sharp. It means that if you have no interaction and you just put the particle in there, it means that it will be 50-50 whether it goes to the right or to the left. So what it means that when we introduce something on the edge, it means that we inject it close to one of the Fermi points. And that is also what have been discussed by Hamilton.
Yeah, so maybe another question, just for my intuition. So your fractional charges are not in the sense that I inject an electron and three separate entities sort of flow off carrying fractional charges. That's not the picture I should be thinking of, or?
Well, I don't think I really understood it.
Well, I guess in the quantum Hall bulk setting, we think of localized, quantized packages of charge that
Yeah.
somehow branch off from into the charges. So that's
Yeah.
quite different from what you have.
Yeah, because now you're talking about the bulk, right? And there you have a gap system. But you can more consider this is what would happen if you have a little swan and you inject something on the edge, and you have an edge interaction going on.
Yeah. So these are quantized charge packages, but their amount of charge is set by dynamics, so to say, not by...
Yeah. The size of the charge is set actually by the interaction between the two edges. So it's like a polarization effect. So if you don't have interaction between counter-propagating modes, you will not get any fractionalization.
And it's also assumed that it's not tunneling.
Yeah, we have no tunneling. We have just interaction between the edges, but a particle can't hop between the edges. You haven't considered that.
So do you picture any experiments where you can see this?
I know there are some. I think there's one. I'm aware of one experiment that I've been done to see this, and it's Steinberg et al., isn't it? Published in Nature Physics, and I haven't read the paper very carefully, but the idea is that they have some kind of, if you had a wire here, you have some magnetic field coming out of the blackboard that makes it possible for you to tunnel an electron down to close to the Fermi points, and then they do some measurements on this, and what they see kind of agrees with this, what they found that I'll suggest, but I can't really see whether they find discuss sharpness of charge. Don't you agree, Hans? It's not clear.
Yeah, I
in
think
this
it
experiment.
measures, they measure currents.
Yeah.
So they cannot say anything about this question of sharpness. They cannot distinguish whether it's a quantum superposition.
So you'd have to do some kind of shot mass or something.
Yeah.
Yeah, there are proposals of noise experiments.
Yeah, I know Weirgethal has suggested actually using a U=1 system where you have constriction like this, and you have something traveling here, and you will get something backscattered. So you kind of change along the bar the width changes, which gives you an effective interaction between the two edges. And yes, just looking at the noise in such a setup too.
So in the case where the interaction is changing as a function of distance, maybe adiabatically, so when they're close together, you have a large screen charge, a large G, and then adiabatically, maybe as it comes further apart, it gets smaller. Do the charges just readjust to what happens in that case?
Well, to be honest, when I read this paper by Berg et al., they kind of use this explanation, but when I saw the pictures and they say that like the width of the bar would change smooth, I would guess that using this kind of adiabatic switching on would be more appropriate to describe it. It's not really clear, but at least in the calculation they use a very abrupt change of edge, or that just suddenly that G just suddenly goes from one and then something different from one very suddenly. It's like a step, and then they kind of.
In that case, is there you have a charge going along and the backscattering at the
Yeah,
at the
yeah.
interface?
Yeah. But at least when I see these drawings that they suggest, I would guess that such a picture would be better, where you just end up with something moving to the right, and you build up this mirror charge on the lower edge.
You can analyze lots of this actually by matching the two widths together, and what we found out later, what we didn't know when we wrote this paper, is that it's a big thesis by Ines Safi, who is the co-author of the famous paper by Schulz and Safi, that explains what happens when you couple leads to the looking at liquids. And she has a more complete analysis of this thing. She never says fractional charge. ever in that paper, but I think that that reference has been ignored, which partly due to that it's a thick thesis written in French without any translation. But the figure captions are actually in English,
yeah, so
and
you can guess what's
if
going
you
on.
try to read it, you can see that there are many of these results actually in that paper.
Have you thought about cold apples? Simulate it or to do it with cold apples?
No, could be interesting. I guess you can make this one-dimensional
I think
systems.
they
Yeah.
have real life looking at
Yeah,
it.
it could be interesting to see what would happen in that case. No, I haven't thought about it.
Questions or comments? If not, then thank you once again. And then for those who are interested, maybe in 3:15 or something like that, for an informal discussion.
Yeah.